Okay, let's get on with some friction. Hopefully, it's not too rough. Hope you got that one. Friction, rough. Okay. If not, that's all right. So, friction. What the heck is friction? Friction is just the resistance to motion an object encounters when it's moving against another object, or really, kind of, we're looking at the two surfaces that are in contact. Now, you might think, okay, well, I get it. Like, I go and try and warm my hands up, right? You rub your hands in winter, whatever it is. You go, okay, I get it. Well, it's a little deeper than that. Kind of under the hood, what's happening with friction is really caused, like, it's really the result of electrostatic forces. So that's like attraction and repulsion between charged particles. That means the protons and electrons that make up all the matter in the universe, which is kind of bizarre. And so, digging a little deeper, we can kind of see this box and we go, okay, yeah, I'm pushing it this way, and friction's kind of opposing it because it resists the motion. It goes the opposite way. And then we kind of got that normal force going up, cool. And then the force of gravity going down, great. And those kind of oppose each other as well. And you go, well, if I blew up this little section kind of right down here, well, we go, okay, so we can see nothing's perfectly smooth. There's this little kind of jaggedy wonkiness down here. And you go, yeah, like in some spots, they're going to kind of catch and like jam against each other. Well, that's part of it. That causes some of the resistance, absolutely. But even more so is the surface of these materials is made up of protons, electrons, and neutrons. And so we can see here that actually there's kind of some settling, and there's some kind of little moments where there's like some attraction, right? Like here's positive, negative, positive, negative. And then even though there's kind of a negative, positive, negative, there's actually some like attraction. And so that causes these two surfaces, kind of in the brown and kind of the grayish green, to really kind of be attracted to each other. And that is really our root cause of friction, which is very bizarre. Kind of under the hood, that's what's really going on. Now, in the kind of the scale that we typically experience friction, though, like what the heck's going on? What really affects how much frictional force I experience opposing me? Well, if you were to go and again rub your hands together, you might find that there's one thing that really makes the big difference is how hard you're pushing your hands together, right? Or in the case of my box here, well, the thing that's determining how hard the green surface and the box are pushing against each other is really kind of this normal force, which is opposing gravity here. In the case of your hands rubbing against each other, it's not really opposing gravity, but there is a normal force going off of one hand towards the other, absolutely, and vice versa. So if you have a bigger normal force, well, you're going to have more friction, okay? The other thing is a measure of the roughness, which we call the coefficient of friction. It's just how rough the surfaces are. And so really that's kind of taking into account all of this stuff we're talking about. It's talking about kind of the jaggediness, but also that electrostatic attraction and repulsion that's really going on there. And we use this Greek letter mu, like this little adorable Pokemon here, Mew, a little old school throwback there. And just one thing to throw out there, there's two ways to write mu. Maybe you just learn to write it like I do, typically like that. Or you could just do a U and just put a little tail on in the front. They look pretty much the same. Both of those work. Just decide on which way that you'll be writing it. So now, thinking of all of this, we go, well, how the heck do we represent this force of friction here? Well, if the surface is rougher, kind of that mu goes up, well, the frictional force should go up. So that kind of makes sense how we get that part of the equation. You go, well, if I have a heavier box, there's more mass, there's going to be more normal force. So if there's more normal force, well, there should be more of them kind of getting smushed against each other. And so we'll experience more friction as well. And so we can see here, if we have more normal force, we get more friction. If we get a rougher surface, we get more friction as well. And so really, this is kind of our handy dandy equation for friction. All right. And typically, in all conditions we'll use in our class, this coefficient of friction has a value between 0 and 1. There's some really weird, kind of wonky situations that can kind of violate that, but we won't really be looking at any of those, okay? So now, let's look at my box, and let's say that my box is moving, but it's moving at a constant velocity. So constant speed, constant direction. If it's going at a constant velocity here, that means that however hard I'm pushing or pulling, really, I should change that to push, is the same force of friction. If one of those was greater, it would be slowing down or speeding up. And so if we have, again, this constant velocity, well, those two, kind of the horizontal forces, must really be matching each other, in all honesty. And on horizontal surfaces, we know that the normal force and the force of gravity are equal but opposite. So those oppose each other. So we know those kind of match each other as well, which is kind of cool. And we know kind of in the back of our head that, hey, well, really the force of gravity is m times g. That's how you find the force of gravity. So when it comes down to it, we could take this beautiful rainbow equation here and kind of reformat it in a way that's a little handier for us on flat surfaces. On flat surfaces, since the normal force is equal to gravity, but gravity is equal to this thing, well, in our kind of rainbow equation, which I've written down here, it's just the same thing again. Well, we can see that, hey, we could just plug in 4mg right here. And so that's all I've done. I just subbed in m and g for the normal force because on a flat horizontal surface, the normal force and force of gravity match. So really, even though this is kind of our generic one that works in more scenarios on flat surfaces, this is really the ultra handy dandy one, and that's kind of it. Now, in terms of what the AP equation sheet shows, they don't show it exactly like I have up here boxed. They show it just like this guy down here. They say that the magnitude of the frictional force is less than or equal to mu times the size of the normal force. Kind of weird, I know, a little bizarre, but they're saying it can be up to that strong. And this kind of includes when it's on slanted surfaces, not just horizontal ones, but like an incline, like if something was sloped like this and we had a box on it. But we'll look at that in coming days. So that's not a right now issue. Now, the last thing I want to mention is this little note here, and it's that technically there are two different mu's. Not like there's mu and mu2, but there are two different mu's actually. And the best way to think of it is imagine you're kind of moving some furniture around your house. You don't want to pick the whole couch up. It's kind of bulky and hard to do that. You just slide the couch in set, right? Now, what's kind of odd is when you go to start moving the couch, you have to push kind of hard to get it started, but then it's easy to keep it going, right? And so the reason for it comes back to this. And it's that in the beginning, these protons and electrons kind of settle in and they kind of like rearrange in a little format where they're close so that the positives are near negatives, the negatives near positives between these two different surfaces here. And so since they've kind of settled in and gotten really comfy cozy, there's a lot of attraction that you have to overcome when you first start pushing the couch, all right? And so in the beginning, it's harder to push. And so that's called the coefficient of static friction. So mu with a little s under it because static means not moving. Once your couch is moving, well, then all of these little kind of bonds that were kind of really close, they've settled in near each other, are broken, right? And since they're broken, you don't have to overcome that attraction as much anymore. And so the coefficient of friction goes down. And so instead of it being static, which means not moving, we have the coefficient of kinetic friction then, which means kinetic is relating to it moving. And so when you start pushing the couch, it's mu sub s in the beginning that you have to overcome, which is greater than this mu sub k, which is when the thing is actually moving. Kind of weird, I know, right? And so all I have here as our last little note is, well, there are technically two different kinds of friction. One for static, not moving objects, which is mu with a little s below it, and one for kinetic or moving objects, which is mu with a little k below it. And this is really related to you sliding the couch. You start pushing it, it's hard to get it moving, but it's easy to keep it going. And that's because in most, and I can't actually think of a situation that breaks this, but really static friction, the coefficient is larger than the coefficient of kinetic friction. All right, that's it.